next quarter, I imagine all of you are taking this math class because you're planning on taking a math class next quarter. If you're planning on going into the 21 series eventually, you're probably planning on taking math 12 next quarter. That's the case. We do have a support for math 12 class you can take. There'll be more information on that particular class on December 1st. So we haven't quite figured out when that's scheduled. If you're planning on taking the 16 series, there's a 16A support class we offer. It's going to be on Tuesdays and Thursdays from 9 to 10:20, and that will be virtual because it's being taught by Claire, who lives in North Carolina. She's great. She's wonderful. So if you're taking 16A this quarter, I definitely recommend trying to leave room in your schedule for that class. It'll be much like this class. It'll most likely be recorded, so you can watch things later if you can't actually attend class. But I do encourage you to sign up for that if you were going to be taking 16A this quarter. In the same sort of way, if you're going into the 17 series, I encourage you to sign up for the one for the 17 series, just 17, which is with Sarah. That will be in person, but also I'm sure she will record things as well, and you can probably attend virtually if that works better for you. So both of those are actually at the same time. So definitely keep that time free next quarter if you're planning on taking 16A or 17A, or sign up for it. If you can't, you can still sign up for it and be in Canvas for that class, even if you can't actually attend in person. There's lots of great resources. Sarah and Claire are both great. They'll help you with all the Calc 1 stuff you could possibly think of encountering. So if you have any questions about that later, feel free to ask, but definitely I encourage all of you, if you're taking 16A next quarter or 17A next quarter, leave room for one of those. If you're planning on taking math 12 because you're eventually going to the 21 series, we'll come back and look on December 1st and see what that's going to be. So just wanted to point that out to you so you all are keeping that in mind and leaving space in your schedule for it. All right, with that said, let's go ahead and get on with the math. So we're going to talk more about graphing rational functions today, specifically graphing rational functions that have slant asymptotes, also known as oblique asymptotes. I've never heard them, well, I had never heard them called that until I started teaching this stuff. I'd always heard them called slant asymptotes, but they're also called oblique asymptotes. Who knew? Not me. So where'd you go? Notes over here. Let's see. Slant asymptotes. So a rational function, which we talked about last time, again, polynomial divided by another polynomial. A rational function will have a slant asymptote exactly if the numerator degree is 1 bigger than the denominator degree. That's the only time you'll ever get a slant asymptote. If the degree is more than that bigger, then you got other weird stuff happening, which we're not going to worry about. And if the degrees are the same, we already talked about how you have a horizontal asymptote. If the degree on top is less, we talked about how y equals 0 would be the horizontal asymptote. So today we're specifically going to focus on the degree on top being exactly 1 larger. If that's the case, your slant asymptote is just going to be a line. So it's going to be like having a horizontal asymptote where we're going to draw a dashed line, except instead of being horizontal, it's going to be slanted. So that's what's going to happen. We're going to have something like y equals mx plus b. And that's weird with the form y, where m and b, I guess, need to be found. I'm going to add some words in there. Need to be found. And to find slant asymptotes, we do everyone's probably second favorite thing ever. We do polynomial division, which I know is really not anyone's favorite thing ever, probably. But it's really kind of the only way to find the slant asymptote is to do polynomial division. So let's look at an example of a function that would have a slant asymptote. Let's say our function was f of x equal to, sure, x cubed plus 4x squared minus 2x plus 6 divided by x squared plus x minus 3. Definitely has a slant asymptote because the degree on top is 3 and the degree on the bottom is 2, and the degree on top is exactly 1 larger than the degree on the bottom. See that case, that we know we have a slant asymptote. And if that's the case, then we have to do polynomial. Now, we're going to do the other things too when we graph something like this, right? We're going to find like the x-intercepts and the y-intercept and the vertical asymptotes. There won't be any horizontal asymptotes because you can't really have horizontal asymptotes and slant asymptotes. You can have one or the other. But we'll find all the usual things. But now let's focus on just finding the slant asymptotes. So we're going to do the polynomial division. So we're going to have, let's see here. I've got this part here, x cubed. Make sure I leave myself enough room here. X cubed plus 4x squared minus 2x plus 6 divided by x squared plus x minus 3. Okay, let's focus in on that just so everyone can see better. Yeah, there we go. Really big. Okay. So the way we do this polynomial division is we ask ourselves, it's kind of like regular division, right? I'm trying to figure out how many times x squared goes into x cubed. But the better way to phrase that is to say, what do you multiply by x squared to get x cubed? And the answer is x. And then we multiply x by all of this. So x times x squared is x cubed. X times x is x squared. X times negative 3 is minus 3x. And then just like with regular division, we subtract. X cubed minus x cubed is 0. 4x squared minus x squared is 3x squared. And negative 2x minus negative 3x is negative 2x plus 3x, which is x. Then we bring down the next term and we repeat the process. Now, what I want to show you here is really the least amount of work you have to do to find the Slant asymptote. So we're about to stop. What do I multiply by x squared to get 3x squared? What do I multiply by x squared to get 3x squared? It's a nice number. Not 1, not 2. It might be 3. It's definitely 3. 3 times x squared is 3x squared. Really, I shouldn't have even done that. I should have stopped right when I got to x plus 3. Because as soon as you get that constant term in your quotient there, as soon as you get mx plus b, you're done. Your slant asymptote is y equal to x plus 3, which is just a slanty line. Going to have a y-intercept of 3, x-intercept of negative 3. Those aren't actually points on our graph, but that's what our slant asymptote would look like. Now, I want to point out, because it is worth seeing why this is true. The reason this is our slant asymptote is because if we finish the division, so again, you shouldn't finish the division. You should stop right there. You say, oh, I got x plus 3, I'm done. But if we continue on with the division, so I'm going to write out the rest of it here. So if I multiply 3 by the rest, so 3 times x is 3x. 3 times negative 3 is negative 9. And if we subtract, we end up getting 3x squared minus 3x squared is 0. X minus 3x is negative 2x. And 6 minus minus 9 is 6 plus 9, which is 15. So here's the idea. When you do this division, what you're really saying is you can rewrite this function, f of x, as the quotient x plus 3 plus the remainder, which is negative 2x plus 15, divided by the divisor, x squared plus x minus 3. Just like you can do regular division, right? If you did division, you got a remainder, you can say, oh, well, this thing is equal to the quotient plus the remainder divided by the divisor. And the idea here is that as x gets really, 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 really big, this part here, since the denominator has a bigger power than the numerator, this part gets small, close to 0, as x gets large. So in essence, that part doesn't matter. And so when we go way, way, way out to the right, or way, way, way out to the left, the graph is going to get very, very, very close to just this part x plus 3 here, because that's the only part that really is going to make a difference. This part here is going to be immaterial. Just like with horizontal asymptote, right? The horizontal asymptote, what we're just saying is, oh yeah, as x gets really, really big, the function gets very, very close to this particular y value. Just here, the y value isn't a value, it's a line. Okay. And that's what we're saying right here. A function will approach, get closer and closer to the slant asymptote for values near negative infinity and or positive infinity. So just getting closer and closer. In practice, what we're going to do is we're going to draw the slant asymptote and just make it so the graph gets closer to it as x is really, really far to the right or really far to the left. Let's look at some examples of rational functions. For each of the following, we want to determine any horizontal or slant asymptotes. Again, have one or the other. You're never going to have both. You can make up a piecewise function if you really wanted to that had a slant asymptote to the right and horizontal asymptote to the left, but that'd be kind of weird, but you could. Technically, you could have both, but like you have to work really hard to have both. So let's look at this first one here. This function, f of x equals x squared over x squared plus 3x plus minus 1. The degree on the top and the degree on the bottom are the same. And when they're the same, that means the horizontal asymptote is going to be the quotient of the leading coefficients. In this case, that's a 1 times x squared over a 1 times x squared. So my horizontal asymptote is going to be y equal to 1 over 1, which is just y equal to 1. Let's go below it. So we look below, x minus 1 over x squared minus 4. Now the degree on the top is less than the degree on the bottom. So we see when the degree on the top is less than the degree on the bottom, That means our horizontal asymptote is going to be y equal to 0. Oops, you can't see that. One year, a student showed me a super cool trick I thought was cheating at first, but I was like, nope, you're right, that totally works. If you really, really want, you could say, well, James, technically, f of x is 0x squared plus 0x, sorry, plus x, 1x, that's a 1x, sorry, minus 1 over x squared minus 4. And so now if you think about the degrees being the same, the quotient of leading coefficients is 0 over 1, which is still 0. They're like, you can do it that way. I was like, it feels a little sketchy, but it works. You can totally do that. It's not, they're not really the same degree, but it's kind of cheating a little bit. No, it's not really cheating, I shouldn't say that. It's just doing something a little oddly normal. Here for x squared over x minus 1, that's where we're going to have a slant asymptote because the degree on top is exactly 1 larger than the degree on the bottom. The degree on the top is the degree on the bottom plus 1. So in this case, we do have a slant asymptote, and to find it, we have to do the polynomial division. So we're going to say that x squared gets divided by x minus 1. There's something to be careful about here. When you're doing this division, if you're missing terms, like I don't have an x term or a constant term, I'm just going to put them in there with 0 coefficients. So I'm going to write this as x squared plus 0x plus 0. Then I ask myself, what do I multiply by x to get x squared? And the answer is x. And x times x is x squared, and x times -1 is negative x. And then we subtract. You can do the thing where you like change the sign. People do that as well. I've never liked doing it that way, but if you like doing it that way, totally fine. X squared minus x squared is 0. 0x minus x is x. Bring down the 0. And now x times 1 gets me x. I'm going to add 1, and that's where I should stop. Stop right there. Don't go any further. That's my slant asymptote. We can't just say it's x plus 1, though. We have to say it's y equal to x plus 1 because it is a line. So our slant asymptote is y equal to x plus 1. Lastly, everyone should be able to show me on their fingers for this last one, what is the horizontal asymptote? I want to see some fingers. I think so, yeah. Interesting. And I've like the doing it like this always seems right. I'm like this. So like that's, I mean, it's the same thing. Just people like, what was that? There was that Quentin Tarantino movie. What was it? Oh, the one where they're killing Nazis. Can't remember what it's called. Where like the guy gives himself away by saying 3, but he does it like this, like an American would, instead of like this, like a German would. And so like it's totally like, what's that movie called? I don't remember. Anyway, it was an interesting movie, but it's very not real because like Quentin Tarantino. Anyway, sorry, this one is y equals 3 because the degree on the top and the degree on the bottom are both the same. And so we take the quotient of the leading coefficients, which is 3 over 1. So horizontal asymptotes, slant asymptotes, we need to be aware of them. We need to look out for them when we are graphing rational functions. So let's look at the next one. So we're going to graph x cubed over x squared minus 9. And not surprisingly, it has a slant asymptote because the degree on top is 1 larger than the degree on the bottom. Let's go ahead and even though normally, well, no, let's go ahead and do things in the usual order. I would do things in this order. So let's find the y-intercepts first. Let me move that cursor out of the way there. Sorry. So y-intercepts, set x equal to 0, solve for y. So if x is 0, y is going to equal f of 0, which is 0 cubed over 0 squared minus 9, which is 0 over -9, which is 0. X-intercepts, set y equal to 0 or just the top. Remember we talked about last time how when you're setting a rational function equal to 0, you can really just set the top equal to 0. So we're going to set x cubed equal to 0 and solve. Well, that's just going to give us x equal to 0. Now, let me ask everybody, for x equal to 0, which just came from this factor over here, what's the multiplicity? It's 3. Which means we're going to bounce or cross at that x-intercept. We're going to cross because it's odd. So we cross. Vertical asymptotes, set the denominator equal to 0. So I'm going to set x squared minus 9 equal to 0. And I do recommend factoring, even though you could totally bring the 9 over and square root both sides. I think it's a better call. Factor, get x minus 3 times x plus 3 equal to 0. So then you get either x equal to 3 or x equal to negative 3. And I will point out that both of these vertical asymptotes are also having odd multiplicities, right? They both have a multiplicity of 1. And when the multiplicity is odd for a vertical asymptote, you get the opposite behavior. So one side up, one side down. Like that. All right, slant asymptote time, polynomial division time. So we're going to do x cubed divided by x squared minus 9. Now I'm going to fill in all the missing x's. So instead of saying x squared minus 9, I'm really going to say x squared plus 0x minus 9. And I'm going to fill in the missing x's here. X cubed plus 0x squared plus 0x plus 0. It might not be super duper necessary, but I would say just do what you're comfortable with. If you're worried you're going to miss things or have things not line up the right way, I do encourage you to write all the terms. So let's see. What do I multiply by x to x cubed? X. Your first thing, if you're finding a slant asymptote, should always just be some multiple of x. In this case, and usually 1x is typically what you're going to get, although not always. X times x cubed is x cubed. X times 0x is 0x squared. X times negative 9 is negative 9x. Subtract. X cubed minus x cubed is 0. 0x squared minus 0x squared is 0. 0x minus 9x is 9x. Now I'll point out, we're actually done. Because 9x has a smaller degree than x squared. We can't do that into that. So our answer is just y equals x. So that's our slant asymptote. I personally think you can skip this number line thing, but that's, if you want to use it, you can. We might come back and look at it in a second. Let's see, did I do anything with it on the actual notes? I guess, fine, we can look at it. So on the number line, if you really want to think about this, you can plot all of your intercepts and all of your x-intercept values and all of your vertical asymptotes. So, right, which it says right here, x-intercepts and vertical asymptotes, that's going to be 0, 3, and negative 3. And then we can determine the sign of our function in each of those 1, 2, 3, 4 sections. There's always going to be one more section, then you have things on the number line. So if we look at our function, I might write it over here just for to have it down here because I'm zoomed in. So f of x equal to x cubed over, I'm going to factor the bottom because it makes it easier to determine the sign. So if we pick a number larger than 3, like 4, 4 cubed is positive, 4 minus 3 is positive, 4 plus 3 is positive, the whole thing's positive. I don't care what the number is. I just care about the sign of the function. So f of x is positive if x is bigger than 3. Right? It works if I pick 4 or 4 million. If I pick something between 0 and 3, like 1, 1 cubed is positive, 1 minus 3 is negative, 1 plus 3 is positive. Positive, negative, positive overall is going to give me a negative. And that'd be true if I picked 1 or 2 or 2.5 or 1.5 or anything between 0 and 3. Pick something between 0 and negative 3. Now, here's what I should really say. At this point, we can use the bouncing, crossing kind of behavior intercepts. We know that at 0, we should cross. We wrote it down up there. So if we're negative on this side of 0 and we're crossing the x-axis, we should be positive on that side. And since our vertical asymptote had an odd multiplicity, if we're positive on this side, it means we're kind of going up, up, up to infinity. And since it's an odd multiplicity, it has to do the opposite thing. So one side's up, the other side has to be down. So we should be negative over here. We can also pick numbers to check. If you pick negative 4 and plug it in, negative 4 cubed is negative, negative 4 minus 3 is negative, negative 4 plus 3 is negative, and the negative times the negative times the negative is negative. Really, though, I think you can skip this and go straight to graphing. So if I plot my points, and I'll try to be fairly careful about plotting this thing. 1, 2, 3, 1, 2, 3. So my vertical asymptotes are positive 3. X equals 3. Oh, yeah, sure, that's fine. And x equals -3. And yeah, let's do this here, sure. And my slant asymptote is the line y equals x. So here's my slant asymptote. I haven't actually graphed anything yet. And then I've got 1 point, 0, 0. But I know a lot about the behavior of my graph. I know that as we go to the right, we have to go negative because we see that the graph is negative between 0 and 3. So we have to go down, 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 down. On the other side of 3, the graph is positive. Or on the other side of 3, we know we have an odd multiplicity vertical asymptote. So if one side's down, the other side has to be up. Now here's where things get a little bit funky. We're going to come down, and then we have to at some point, we can't just go down like we have a horizontal asymptote. We have to go down and essentially turn around at some point and get closer and closer and closer to that slant asymptote. Same sort of thing is going to happen on the other side. We go to the left, we're going to go up, 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 up. Because we don't have any other choice. And then on the other side of this vertical asymptote, we're having the opposite behavior. So we're going to be down here somewhere and then coming back up and then eventually turning around and going that way, getting closer and closer and closer to the slant asymptote. Can you cross the slant asymptote? Yes, we did. Right there, we crossed it. So you can definitely cross the slant asymptote. We try not to if we don't need to, but sometimes you need to. Okay, any questions about this example? Or observations or thoughts? I have one observation. I will point out that this function is an odd function. If you took your original function, x cubed over x squared minus 9, and replace it with -x, you would get -x cubed over x squared minus 9, which would be the negative of the original function. Which, if you think about it, even though it's kind of funky to think about, if you rotated this thing 180 degrees around the origin, it would look the same. In fact, oh, you know what? I can actually do it. If you rotated 180 degrees around the origin, it looks the same. That's kind of great. I'm really pleased about that. It just, I'm super happy about that. It makes me really happy. I can do that. You can't really do it with a flip though. So anyway, it is an odd function. That's kind of neat. Let's look at the next example, which is a little more interesting, I think. So we're going to graph f of x equal to x squared minus 4 over x minus 1. Again, definitely has a slant asymptote. But let's fill in all the other pieces first. Let's find the y-intercepts. So x equals 0. Y is going to be 0 minus 4 over 0 minus 1, which is just 4. Or -4 over -1, which is 4. X-intercepts, we've got setting x squared minus 4 equal to 0. We're going to get x minus 2 times x plus 2 equal to 0. So we're going to get x equal to 2 with a multiplicity of 1, and x equal to -2 with a multiplicity of 1. So they're both going to cross. They both have odd multiplicities. Right? They both have odd multiplicities. That's also why I really do encourage the factoring here instead of doing like x squared equal to 4 and x equal to plus or minus the square root of 4. If you do the factoring instead, it better allows you to see what the multiplicities of each intercept are going to be. So I really, really, really can't stress enough. Factoring is almost always the better way to go. Not always, but almost always. For the vertical asymptotes, pretty not too terrible. We're going to set the denominator equal to 0. And solving that's a straight shot. You just get x equal to 1. I will point out this does have a multiplicity of 1, which means we're going to have the vertical asymptote that does either up on the left and down on the right, or vice versa. Or down on the left and up on the right. You have the opposite behavior, is what I always like to think of. Odd multiplicity, opposite behavior. Let's skip the number line for now. Let's go straight. Oh, let's skip the number line and do the horizontal, the slant asymptote maybe. So let's do some polynomial division. So I'm doing x squared minus 4. So x squared plus 0x minus 4 divided by x minus 1. So let's see. X goes into x squared, or x times x gives me x squared. So then multiply x squared times x, or x times x, x times x is x squared, and x times -1 is negative x. Subtract. 0. 0x minus x is 0x plus x, so x. Bring down the minus, I can bring down the -4, sure. Multiply x minus x, multiply x by 1 to get x. So we're going to get a +1 there, and that's where we should stop. Y equals x plus 1. That is our slant asymptote. I do want to point out, I am going to keep going here for just a second because I want to show you again, kind of just to remind you of what's really happening. Well, actually, I'm going to wait. No. So we kept going here. So 1 times x is x, 1 times -1 is -1. If we subtract, x minus x is 0, -4 minus -1 is -4 plus 1, which is -3. So what we're really saying here is this x squared minus 4 divided by x minus 1 is really equal to x plus 1, the quotient, plus -3 divided by x minus 1. That's what we're saying when we do this polynomial division. And so when x gets really big, or really negatively big, this fraction here, -3 over x minus 1, gets super duper small. And so essentially the graph becomes very close to the line y equals x minus 1, x plus 1, sorry. That's the idea. Yeah, let's skip the number line. Let's go straight to just throwing the things on the graph. So let's see, what do I got? I've got a y-intercept of 4. 1, 2, 3, 4. I've got x-intercepts of +2 and -2. I've got a vertical asymptote of x equal to 1. Okay, do that. And I like to have asymptotes in a different color, although you don't have to. There's x equal to 1. And then my slant asymptote of y equal to x plus 1. So I'm just going to think about drawing the line y equals x plus 1, which would have a y-intercept of 1 and an x-intercept of -1. These aren't actually intercepts on my graph. They're just the way I'm going to help myself draw the slant asymptote. So I'm going to go through that point there and that point there and draw a slanty line, but dashed. Oh, I should be using my ruler. So there's our slant asymptote, y equal to x plus 1. Okay, I've got all the features I could possibly put on there. I mean, that's not true. I could draw more points if I wanted to. I've got all the features I'm going to put on there. Now let's try and draw it. So starting where I recommend starting at my y-intercept, if we move towards the right, towards this vertical asymptote, which way do we have to go? Up or down? Got to go up. We can't go down because we can't cross the x-axis because we don't have an x-intercept there. So you can never cross the x-axis unless you have an x-intercept. So we have to go in this direction. On the other side of this vertical asymptote, we are down here. Now, I will say, if you don't like doing it this way, saying, you've got an odd multiplicity, so you're going to be going the opposite way, you can do the number line stuff. You can say, okay, on my number line, I'm going to my x-intercepts, so -2 and 2, and my vertical asymptote 1, so -2, 1, and 2. Don't put 0 unless it's actually an important point. I know it's really comfortable to put 0 on there, but you don't need it. And you could go ahead and look at your function and say, okay, my function is x minus 2 times x plus 2 over x minus 1. And here's what I really want you to see. Each of these factors has what power? I know I didn't write it. This much, 1. Each of these factors has a power of 1. Or more importantly, each of these factors has an odd power. So whenever you change from one side of one of these points to the other side of one of these points, you're going to change the sign. If I pick up something bigger than 2, like 3, 3 minus 2 is positive, 3 plus 2 is positive, 3 minus 1 is positive. If I pick something between 1 and 2, the only thing that's going to change is the x minus 2 factor. If I pick 1.5, 1.5 minus 2 is negative, but the other two factors are still going to be positive. 1.5 plus 2 is positive, 1.5 minus 1 is positive. So since that's the only one that's going to change, the whole thing is going to change signs. And the same thing is true when we go to the other side of 1. If I pick something like 0, now 0 minus 2 is still negative like it was over here, 0 plus 2 is still positive like it was over here, but 0 minus 1 is now going to be negative instead of being positive. So we have a negative, positive, negative. The whole thing is positive. And then once again, if we go to the other side of negative 2, then everything's going to change again. Or I should say that one thing's going to change again, and you're going to get negative, negative, negative. There's this pattern that you see when you do this kind of work where if the powers are all odd, you're going to change signs every time you cross from one thing to the next thing. Whereas you have some even powers, like when you bounce, the sign doesn't change. We'll see that in another example. So if we could think of, okay, great, we're bigger than 1, so the whole function is negative. So we're down here where it's negative. And then as soon as we get to 2, we're going to cross, which we knew we were going to do because it's an odd multiplicity x-intercept. And then if we keep going to the right, the only choice we have, the only thing we have left to kind of do is get closer and closer to our slant asymptote. So when you've run out of features, when you've run out of vertical asymptotes or intercepts, that's when you have to be like, okay, the asymptotes, the horizontal or slant asymptote is the last thing we're going to get closer and closer to. Okay. On the other side, going back to my intercept, if I go to the left, I'm going to go down to the left, I'm going to hit that x-intercept there and then cross and then just get closer and closer and closer to the slant asymptote. So what we're saying over here is our function, f of x, so I'm going to write down here just to see it, which is equal to x squared minus 4 over x minus 1. Or as I like to write it, as I did write it, x plus 1 plus negative 3 over x minus 1. Way over here, when x is like, 10, you're getting essentially x plus 1 minus 3 over 10 minus 9 minus 3 ninths minus 1/3. So you're just a little bit under the line y equals x plus 1. And as x gets bigger and bigger and bigger, we just get closer and closer and closer to that line. That's why it's a slant asymptote. Okay. So this is kind of the deal for each of these. We're just going to do the same sort of thing over and over and over again. You're going to find the y-intercept, you're going to find the x-intercepts, you're going to find the vertical asymptotes, you're going to find the slant asymptotes. Or horizontal asymptotes if there's horizontal asymptotes. All of these examples are slant asymptotes because that's what we're talking about today. But if the degree on top and the degree on the bottom were the same, you'd be finding a horizontal asymptote. All right, we got time. We got plenty of time. So much time, he says right now when he has time. Ooh, yeah, this next example is a good one. Oh, yeah, that's fine. Okay, sure. Let's do, is this the one you have next? X minus 2 cubed? Okay. I kind of want to do the other one next, but we'll do this one fine. So same deal. We're going to find all the stuff. So y-intercept. Oh, yeah. All right. So if we plug in x equal to 0, we're going to get y equal to 0 minus 2 cubed over 0 minus 0 plus 6. That's going to be a negative 8 over 6, which is a negative 4/3. Now, this function has an issue, which we need to address, which I haven't talked about for any of the other ones because it has an issue. But really, when you're graphing something like this or plotting, doing something like this, what we really should check for is if any of the factors cancel. So I'm going to factor the denominator and say this is equal to x minus 2 cubed over that denominator factors as x minus 2 times x minus 3. And I can cancel one of the x minus 2s. So what I'm actually going to get is that this is equal to x minus 2 squared over x minus 3. This one's a little problematic because now the problem is x is not allowed to be 2. We canceled an x minus 2 and an x minus 2. So when you cancel an x minus 2 over x minus 2, what that means is we have a hole. There's a hole at x equal to 2. So all we're going to do is we're going to pretend like we don't care about that really. We're going to fix that part at the end. We're going to go along our merry way. We're going to do everything else like we normally would. So if I was thinking about x-intercept, but now I should say we're going to go along our merry way, but we're going to look at this as being our function now instead of this more complicated thing where we didn't cancel things. So now if we look at this, if I try to find the x-intercept, I'm going to set x minus 2 squared equal to 0, and I'm going to end up getting x equal to 2, which is kind of a bummer. because it's not really going to be an x-intercept because we know we're going to have a hole there. Still going to be okay though. Vertical asymptote is where this thing is especially important to recognize what's happening. So if we look for the vertical asymptote, if we weren't being careful and just set the original denominator equal to 0, we would get 2 and 3 as vertical asymptotes. And they're not. 2 is not a vertical asymptote because when we canceled, in fact, when we factored and canceled, we no longer have an x minus 2 in the denominator. So you really, when you're looking for the vertical asymptotes especially, we need to make sure we have canceled any factors before we do that. So here we're just going to set x minus 3 equal to 0, and we're going to get x equal to 3. And I should note over here, right? X equals 2. I'm going to write some question marks and be like, well, we're going to check back on this. It's going to be a little weird. Let's see. I found my y-intercept. It's totally fine. X-intercept we'll deal with. Vertical asymptotes, x equals 3. We still need to find the last thing, which is going to be a slant asymptote. Because the degree on top is certainly 1 bigger than the degree on the bottom. You definitely don't want to do this division, meaning we don't want to write it as x minus 3 dividing into x minus 2 squared. That's not going to go well. We need to multiply out the x minus 2 squared to actually be able to do this. So instead, we're going to do x minus 3 into, let's see, x minus 2 squared is x squared minus 4x plus 4. And then we say, okay, x times x gets me x squared. X times x is x squared. X times negative 3 is minus 3x. Subtract. Negative 4x minus negative 3x is negative 4x plus 3x, which is negative x. Sorry about that. Thank you. And then bring in the 4. And x times negative 1 gives me negative x. And as soon as I write that negative 1, I stop. That's my slant asymptote. There's our slant asymptote. Y equal to x minus 1. Great. So now we're going to start graphing it. And we're just going to pretend like the hole is not a problem we're going to deal with in a minute. So on our graph, so here's how holes really work. You take your thing that's factored and canceled, and you say, okay, well, if I could plug in 2 to this, what would I get? And in this case, you would get 0. If I plug in 2, 2 minus 2 is 0. 0 over 2 minus 3 is 0 over negative 1 is 0, which is just 0. Sorry, same words there. So to deal with a hole, plug in the problem point. See the words I'm writing, maybe, yes. Plug in the problem point to the simplified version of the function. So in this case, our simplified version is f of x equal to x minus 2 squared over x minus 3. If we plug in 2, you get f of 2, which is 2 minus 2 squared over 2 minus 3, which is just 0 over negative 1, which is 0. Something I want to say. You might be wondering why we have to do this. And the reason we have to do this is because we actually plugged it back into the original version. We plugged into 2 here, you would get 0 divided by 0. And 0 divided by 0 is not 0. It can be anything. So that's why we have to do this work. Because 0 over 0 is what's called an indeterminate form or undefined. But it's a kind of different thing than undefined. So yeah. All right, let's graph all the things. So we have a y-intercept of negative 4/3, which is a little bit more negative than negative 1. And we have x-intercept. Well, we don't have an x-intercept, but we do have a hole at the point 2, 0. There's a hole there. We have a vertical asymptote at x equals 3. And we have a slant asymptote at y equal to x minus 1. And I didn't grab my slant asymptotes in different colors. Oh well. All right. So we start at this. This actually would probably be one of the times where we maybe should use the number line. I'm not going to lie. Things are looking a little dicey here. So if we look at our number line real quick, the numbers that should go on the number line are my vertical asymptotes, which were 3. And my x-intercept, even though I didn't have it, it's probably still worth putting on there just to be careful. I'm going to put x equals 2 on there as well and see what happens. So I look at my simplified version. If I pick something larger than 3, like 4, positive on top, positive on the bottom. Pick something between 2 and 3, like 2.5. 2.5 minus 2 is positive. Positive is still positive. But 2.5 minus 3 is negative. So I have a positive over a negative. It's going to be negative. On the other side of 2, if I pick something like 0, when I pick 0, the whole thing's negative. I can still check. 0 minus 2 squared is a positive 4. 0 minus 3 is negative. So yeah, it's negative over here. So even though we don't have an x-intercept at 2, it's still kind of doing this bouncing thing at 2 because the x-intercept that we didn't have came from a factor with an even multiplicity. So we'll try and graph this thing. We'll start at my y-intercept. We'll go towards our non-existent x-intercept, and then we're going to bounce off. Stay negative. So stay positive. On the other side of x equals 3, we're going to be going up because it's positive over there. So we have to be going this way. And then we have to turn around. And I would say I've drawn that a little not greatly because it kind of looks like it's curving back around that way. It should be going not that way. It should be going up and up and up like that. Definitely the function should not curve back on itself. Otherwise it wouldn't be a function because it failed the vertical line test. All right, and then to the left, I think we can see what's going to happen. It's just going to go closer and closer and closer to the slant asymptote. Poles are kind of weird. They don't come up super often, but they do come up occasionally. So just be aware if you've got something that looks like it should be factored, you probably should factor it just to see if any factors cancel. And then deal with the simpler thing. Also, it's much nicer. It's nice that we didn't have to multiply out x minus 2 cubed to then do the polynomial division. That also would have been not great. So we definitely benefited from factoring and canceling. It is a good thing to do when we do these kind of problems. I believe in this module on Canvas, I have a video from, I think last time I taught this class, doing more examples with holes in them. So if you want more examples with holes in them, you can go watch that. I would recommend it. Let's look at our, I guess, last example. Yeah. Yeah, I mean, I'd like to say we can do more, but I doubt we'll have enough time to do more than this. So here is our last example. F of x equal to x cubed minus 3x squared over x squared minus 2x plus 1. And because we should, let's factor as much as we can. So on top, I can factor out an x squared. I'm left with an x minus 3. On the bottom, x squared minus 2x plus 1 factors as x minus 1 times x minus 1. And when you have repeated factors, you really should write them as something to a power. So instead of writing this like this, I'm going to write this as x squared times x minus 3 divided by x minus 1 squared. I'm going to make the statement I made last time again. This unfactored version, this is really good for all the y stuff. This is good for finding the y-intercept and any horizontal or slant asymptote. Whereas the factored version is really good for finding the x stuff. This is good for finding the x-intercepts and the vertical asymptotes. Oh, sorry, you can't see that. Too zoomed in, but I want to be zoomed in so you can actually see what I'm writing. So let's find the y-intercept. Y-intercept. Oh, and I should point out, right, we factored and nothing canceled. Totally fine. Still worth factoring. So to find the y-intercept, set x equal to 0, plug it in, and you're going to get f of 0. Again, I'm going to plug it into the not factored form. I'm going to get 0 minus 0 over 0 plus 0, sorry, 0 minus 0 plus 1, which is 0 over 1, which is 0. For the x-intercepts, we're going to set the top equal to 0. And I would set the factored top equal to 0. So if we set x squared times x minus 3 equal to 0, it's a real straight shot, excuse me, to see that you get x equal to 0 with a multiplicity of 2, meaning we're going to bounce, and x equal to 3 with a multiplicity of 1, meaning we're going to cross. For our vertical asymptotes, well, tote, singular, we're going to set x minus 1 squared equal to 0, and we're going to get x equal to 1 with a multiplicity of 2, meaning that for our vertical asymptote here, both sides are either going to both go up or both go down, right? So because when the vertical asymptote has an even multiplicity, you get the same behavior. So here we're going to have at our vertical asymptote either something that looks like up on the left, up on the right, or something that looks like down on the left, down on the right. I want to contrast that with all the other vertical asymptotes we've seen that have had odd multiplicity, and you've had one side up, one side down. So when the multiplicity of the vertical asymptote is odd, you get the opposite behavior. When the multiplicity of the vertical asymptote is even, you get the same behavior, up, up, or down, down. That's the way I like to think about it. Or you can test extra points, right? That's always an option. It's just not my favorite option. As you might have gathered, I'm trying to graph this with plotting as few points as possible every time, which is what I would kind of encourage for you all, right? I don't want you to have to plot a million points. You certainly can. You're always welcome to plot a few more points. But the idea here is to graph these things as efficiently as possible so that we can do them and get a general sense of what the graph looks like without having to get super duper detailed. All right, let's see. Last thing is the asymptote. So I don't have a horizontal asymptote because the degree on top is bigger than the degree on the bottom. I definitely have a slant asymptote because the degree is 1 larger. If in your future you see something where it's like x to the 4th over x squared, that doesn't have a slant asymptote, it doesn't have a horizontal asymptote, it has something else that's kind of weird that we're not going to worry about. So don't worry about if the degree is too big on top, that's just a whole other situation. But if the degree is exactly 1 larger on top, that's when you should be like, oh yeah, there's a slant asymptote, they probably want me to find it. So slant asymptote. Let's do our polynomial division. And again, I want to use the unfactored form. So I'm going to do x squared minus 2x plus 1 into x cubed minus 3x squared. I probably should write the 0x and the 0, although I might not actually need them. Still good to write them. So I multiply x squared by x to get x cubed. I multiply x by everything over here, so I get x cubed. X times negative 2x is negative 2x squared. X times 1 is x. We subtract. X cubed minus x cubed is 0. I'm not going to write that. Negative 3x squared plus 2x squared is negative 1x squared. And 0x minus x is minus x. Bring down the 0. Do it again. What do you multiply x squared to get negative x squared? Negative 1. And then we should stop. Slant asymptote, y equal to x minus 1. You never have to finish this polynomial division. You just have to get to the place where you have something times x plus a constant. That's all you need. As soon as you got 2x plus 1 or 3x minus 5 or whatever x plus whatever, that's the end of the story as far as we're concerned when you're finding a slant asymptote. So you don't need to do the rest of this down here. I think we put it all on the graph now. Let's see what we've got. We've got a y-intercept of 0. We've got x-intercepts of 0 and 3. We've got a vertical asymptote of positive 1, written in red. And we've got a slant asymptote of y equal to x minus 1. So that would have a y-intercept of negative 1 and an x-intercept of positive 1. Again, those aren't actual intercepts on my graph, just guidelines to help me draw this slant asymptote. So I'm going to draw the line there. Again, I should use my ruler, but I forgot about it, so oh well. Slant asymptote should be a straight line. Okay. Finally, we try to graph the thing. So this is, again, a situation where when you have the origin as your y-intercept, it's hard to know if you're supposed to go up or supposed to go down. There's no good intuition here. I don't, and so you might think, you'd be wrong, but you might think we should go up because I don't want to go down because I don't want to cross the slant asymptotes. We actually are going to go down, cross the slant asymptotes. So if you're not sure which way to go, this is when you want to test another point. Or use or you could do the number line. Okay, fine. Talk me into it. We do the number line thing. So on our number line, so maybe the number line isn't as terrible as I said it was. It's probably pretty useful. I just don't like doing it because I'm lazy. But on our number line, we're going to put all the x-intercepts and the vertical asymptotes, which we already have on our graph. So 0, 1, and 3 are the things that should go on our number line. And then we're just going to test the point. So pick something, I should write the function down, the factored version of the function, which is x squared times x minus 3. We're almost done, I promise. So picking something bigger than 3, like 4, positive, positive, positive. Picking something less between 1 and 3, like 2, positive, negative, positive. Picking something between 0 and 1, like a half. Positive, negative, negative, but we square it so it's positive. So positive, negative is still negative. And then finally picking something less than 0, like negative 1, positive, negative, positive. The whole thing is negative. This is showing us that at 0, we're getting a bounce like we expected. At 3, we're getting a cross like we expected. And at 1, the vertical asymptotes are both going negative. They're both going down, 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 down. So this is going to look like this. Down. And on the other side, also going down. And then we're going to come towards that point 3, and we're just going to cross through. And on the other side of this intercept, we're going to be going down. So we're bouncing, we're bouncing, we're bouncing. And then you kind of just have to get closer and closer to the slant asymptote. So at some point, you have to kind of weirdly turn around-ish. Like, yeah, you don't just want to kind of come like that. You want to be like that. It's kind of weird. It's worth graphing on Desmos just to take a look at it, see what it looks like. But that is our final product. All right. I see you all on Friday.